Hello everybody, welcome to this webinar on 3D sound. My name is Pontus Larsson and I work at the company Ictech, which is a company in systems and software development, which offers end-to-end business solutions and consulting services in all stages of the development process. And we also conduct research both internally and in collaboration with partners in publicly funded projects. And I'm actually going to talk about some of these projects today in this webinar, in the end of the webinar. And a little bit about my background. I have a PhD in acoustics. And during that research, I actually focused a lot on topics of today. 3D sound and how you can use that for virtual reality applications, for example, to enhance sensation of immersion and presence and stuff like that. And after my PhD, I worked or am working in the vehicle industry. Worked a lot with human factors and human-machine interface interaction research. And we're also been involved a lot in sound design for vehicles, for cars and for trucks. And actually in the end of the webinar, I'm going to talk about a project where we combine these things, both 3D sounds and vehicles, and projects that concern remote operation of road vehicles. But more about that later. Let's dive into the webinar. Well, not just yet. I'm going to ask you to put on your headphones during this presentation, and it's not just because I want your full attention, but it's also because the things I'm going to demonstrate here today is 3D sound played over only 2 channels, so over headphones. So to experience the effects of the demos here, you need to put on your headphones with the left headphone on the left ear and right on right ear, as you know. The agenda for today looks like this. A little bit about the concepts and definitions of different things first. Then I'm going to go into the basics of human spatial hearing. And what is 3D sound? What can, how can it be rendered and technologically implemented? What the advantage is, and some basics about 3D sound technologies, and then finally go into some different applications. But to start with, what is actually 3D sound? Well, I didn't really find a crisp definition, so kind of invented my own here. But it's about reproducing audio in a way that replicates the way we spatially hear sound in the real world. So recreating the spatial aspects of our auditory system, basically. You could call it VR audio, virtual reality audio, or virtual auditory virtual environments. And today I'm going to mainly talk about technologies that can achieve this sensation, this kind of perception using only 2 channels, left and right. You know, we have a left and a right ear, and by being able to simulate the sound pressures at left and right ear, we can actually create this spatial sensation of everyday hearing. I'm also going to use the concept or the word terminology auditory display, which is a fancy word for saying for the use of sound to communicate information between the computer or a system and a user. Well, there's a variety of projects that uses products that use sound, of course. Cars, which is a field which I'm familiar with. They have a lot of information and warning sounds, for example. They have speech interaction, navigation prompts, to communicate all the advanced systems that we have in our vehicles today. computers, smartphones have all these types of feedback sounds and notifications and so on. There's also a type of auditory display. Aircraft, of course, quite vital for the pilot to get warnings in time, information in time, and here you often use speech feedback to be able to communicate very clear message to the pilot and know what the situation is all about. It's also coming sound more and more into home appliances, stoves, tumble dryers and stuff like that, to communicate various states of the machine to the user. One field which is, of course, very good use of sound is assistive devices for visually impaired. So on the far right here you see something which actually is an auditory display. It's a little device that you put on your cup. So when you fill up the cup with coffee or something, you will get the sound feedback when the height of the liquid or the amount of liquid reaches a good amount, so you don't overfill your cup. So of course a very simple feedback or auditory display, but imagine you can have all these kinds of auditory feedbacks in different situations as a visually impaired to help you in your everyday life. So today we're going to talk about 3D auditory displays, you could say, of various sorts. But to be able to understand why and how this functions, we need to know a little bit more about human spatial hearing. And we could start by asking the question, how can we tell where a sound is in relation to ourselves? Well, we use our auditory system uses different so-called cues to resolve where a sound source is in relation to us. And the main cues that our auditory system uses are the interaural level differences and interaural time differences. So if you have a sound source positioned like in the image to the right here, the left ear will receive sound which is a little bit quieter and arrives later compared to the right ear, which will be a little bit louder and arrive a little bit earlier. So by use of these interaural or between ears, if you like, differences, the auditory system can resolve the basics of where this sound source is. There's sort of the strongest cues. But the auditory system faces a problem if we have this situation on the right here. These two situations will result in more or less the same interaural or between ear cues. So to be able to resolve this situation, we have our little outer ears, the pinna, which will shadow the sound a little bit, will muffle the sound when the source is behind us. So we get a sort of a spectral difference between these two situations, and not this interaural kind of cue, but it's more a spectral cue, which we have learned then to use to discriminate between these two situations. One thing that also helps sound source localization to a great extent is head movements. So if we have the situation to the left here, we won't have any interaural cues at all. Same level and same time, both left and right ears. So it's hard to tell if the source in front or behind us. Of course, have the spectral cues of the pinna, but it's not that strong especially if we haven't heard the source before. But if we start to rotate our head, we can easily then tell if the source, then these differences start to occur, and then the auditory system can rule out, so to say, where the source is, if it's behind or in front of us. So in this case, we found out that the change in intraoral cues match the front source position. So head movements, that's something maybe you're not aware of it in everyday listening, but you use it all the time just to be able to localize sources, move your head a little bit. Another situation is when we have height cues, or we have sources that move above us. For example, a helicopter or something, which hovers above our head, and then it travels a little bit behind us maybe, and lowers its height. And we don't have any intraoral differences either. And again, we have some spectral cues here that the auditory system can use to resolve where the source is in terms of height. It's again the pinna which kind of creates these spatial cues, but it's the inner part of the pinna, the concha, which sort of works as a notch filter, a filter which has a frequency which depends on the height of the sound source. So you can think of it when you move a noise source like a hairdryer up and down your head, you can clearly hear this sweeping effect that this concha thing causes. And we actually have a little demonstration of how it can sound here. So as you probably heard this kind of sound when the hairdryer was moving, and that's caused by this concha of the pinna. So that can tell you where the sound source is in terms of height. Now you might have heard also in this demonstration that it actually felt as if the hairdryer was actually there behind your head, moving up and down and around your head. And what was demonstrated here is actually, it's a sort of a 3D sound technology. It was a binaural recording. So binaural technology is the basis of the 3D technologies that I'm going to talk about here today. So binaural recording is something which can be used to mimic spatial hearing. And what it is basically based on these kind of dummy heads that you see on the pictures here. This is basically different microphones, very advanced form of microphone, but they are microphones. So a dummy head, and they all had microphones in their left and right ear canals, or on the entrance of the ear canal. There's a lot of different variations that you can see here. For example, the leftmost there is called KEMAR, which was one I used in my math thesis project actually. The HMS to the second there is something which is used in vehicle industry quite a lot to capture the sound field in cars and trucks, and to be able to reproduce it later on and to listen to what it actually sounded like being in that situation. Because that's what you can do. You can put it in any environment and record sound and play it back later on over headphones, and it will sound as if you're actually there in that environment listening. These are often pretty expensive, but you can do this in a much cheaper way using these small microphones. This is not headphones, this is microphones actually, which you put in your ears and you go out and record it using your smartphone or whatever portable recorder you have. And you can go back and then go back home and listen to the result, and it will sound like as if you were there in that environment. So it's a pretty simple but effective and quite a neat way of capturing a sound field. I will now play you some demonstrations of this, some further demonstrations of this. This first one is using this Neumann head, as you see here. And yeah, I'll just play it here. All right, so I hope you get how it works now. It's pretty simple but effective. Here's another example. I won't say so much about it, but now that you know how it works, you could close your eyes and really try to imagine yourself being in this situation, listening to this sound moving around your head. Let's play this next example. Okay, these were recordings. They are of course static. You cannot change them. You cannot move the sound sources around your head as you would like to in a virtual reality application, for example. So in order to be able to do so, to be able to have the flexibility to create your own virtual sound field, we need something called head-related transfer functions, or HRTFs. So maybe then you need to know what a transfer function is, which you might know if you studied signal processing or similar. But let me try to explain it in a short way. Well, a transfer function is something which mathematically describes the relationship between the input and the output of a linear system. So you can see the transfer function as a filter that describes the linear system, and that you can recreate the response of this system by inputting any signal, for example a sound in our case, into this filter or this transfer function, and observe what comes out from the output. For example, you could listen to the sound from the output. In our case, we have two transfer functions that we want to have or find out. One from the source, the loudspeaker, in our case here on the picture, to the left ear, and one from the loudspeaker to the right ear. So by knowing these two head-related transfer functions, we can simulate the sound pressure at the left and right ears in a situation where the loudspeaker is playing sound from this position that you see in the picture. And these transfer functions, they contain all the cues that is needed for spatial hearing that we talked about earlier. So the differences, the level differences, the time differences, the spectral cues, and so on. So in other words, if we would input any sound to these head-related transfer functions, these filters, and listen to the result, the output through headphones, it would sound as we would listen to this loudspeaker in real life. Now, to get hold of these transfer functions so we can actually use it in a technical system, you need to measure them. You don't need to, you can calculate them also, but the most common method today is to have measured transfer functions. And you measure them by basically sending a measurement signal. It could be a noise or a sine sweep, a broadband signal in any case, to the loudspeaker. And then you use microphones in the ears of the subject or the dummy head to pick up the sound. So you get two recorded measurement signals. Then you convert it into frequency domain, usually by using FFT, Fourier transform. So you have the frequency domain signals or corresponding vectors for these measurement signals, recorded signals. And then you calculate these HRTFs by dividing the output by the input. So there you have everything to be able to recreate the sound pressures at left and right ears. For this loudspeaker position only, though. So this can only simulate one source position. We want to be able to move the source around our head and yeah, recreate all sort of acoustic situations. So then you actually need a lot of loudspeakers and measure all the HRTFs for all these loudspeakers. Not just in the horizontal plane as I show here, but also speakers above you and below you. So there's a lot of speakers and a lot of measurements. But when you have that, yeah, here's a little animation, how it can be done. You go through all the speakers, send out the measurement signal and pick up the microphone signals, and you do the calculations in your measurement software, and so on. And eventually you collect all these HRTFs into a catalog, which then has a collection of HRTFs corresponding to all these different source and source positions. So once you have that HRTF catalog, how do you do to render the virtual sound field? Well, it's basically like this. On the left here you see the virtual sound that we want to render. It looks a bit like before. We have the head angle as input here as well. As I talked about earlier, the head orientation is a strong cue for localization as well. So we want to take that into account. But basically the combination of a sound source angle and your head angle, you get at some kind of total angle, which you use then to pick out the correct HRTF pair, one for left ear and one for right ear. And you put those HRTFs into this filter system here, the purple and the pink one here for left and right ear, or right or left ear. Then you input your sound that you want to render, that you want to place around the listener or the user. You input that into those filters, so you get two channel output from these filters. Send it to headphones, and then it will sound like if the sound came from that position. So it's fairly straightforward. The trick is here that the user can turn his or her head all the time, so you need to update the HRTF selection all the time, basically, and the sound source can move as well. So the trick here is to do this selection and updating of the HRTFs in real time as smoothly and as quickly as possible to avoid any latency effects and sort of create a natural and smooth experience. There are things which I have left out a little bit here. To be able to do this really good, you also would need to remove the loudspeaker response, the microphone response that you have used to measure, and also take into account the response of the headphones here to be able to really do this super well. But it works pretty well if you don't do this also. And one thing which really affects the perception, though, is what type of HRTF you listen to. I mean, you've seen different types of dummy heads, and you can also measure different subjects, different persons. Ideally, you should listen to your own HRTFs. But it's a bit complex to do these HRTF measurements because you need a large loudspeaker array like the one you see here. You need to measure with high enough density, spatial density of the speakers. So in this case, you probably need to rotate the listener a little bit and perform all the measurements again to get high resolution, basically, in the spatial domain. This is another solution you can do. If you don't have so many speakers, you could rotate the head instead on a little robotic arm that you see to the right here. Maybe feasible if you have this kind of dummy head. Maybe not so feasible if you have a human subject and want to move her or him around this with this robot. But anyway, this is not something that all developers do, of course, measure their own HRTFs, but rather you have a large set of different HRTF catalogs. You can download these for free many places, and I guess the idea is to select the HRTF which you think works best for your ears. So pick a measured HRTF that corresponds to your own head dimensions and your own ear dimensions and so on. But there are also HRTFs which are sort of considered to be working for many people. So that's what these main 3D media streaming services like YouTube and so on are using when they render their 3D sound, that company's 3D video streaming services. Yes. Now, things are a little bit more complicated in real life, and we talked about so far. In a normal situation, you will have effects also from the room or any surface that is close to the source which emits the sound. So in this picture, you see a speaker here to the right, speaking to a person sitting in the audience there. You get a direct sound, of course, first, and that's the one we have tried to render so far. But in addition, you will hear also, as the audience member there, you will hear a lot of reflections from the surfaces of the room. These are just a few reflections corresponding to the first order reflections, the blue ones here, and the second order reflections. But in real life, there will be a lot of reflections from the room that you will also hear, and that will be part of the experience of the room. So if you leave out all these things, it will be a very dry and unrealistic experience. So in order to get a good perception of a virtual environment or remote environment, you would need to include some kind of auralization, where you not just render the direct sound, but also the reflections, and as well as the late reverberation of the space that you want to simulate. And ideally, all these reflections that you see should have their own. They come from different directions, of course, as well as the direct sound. So they would need to have their own HRTF rendering on them. Which will be quite computationally intense if you want to simulate all the reflections. So often for later reflections and the reverb, you apply a bit of simplification to make it feasible to run this in real time. Auditorization, the word itself was defined in '93 by my former professors and colleagues at Chalmers, which is the process of rendering audible the sound field of a source in a space in such a way as to simulate the binaural listening experience at a given position in the model space. So basically you try to recreate the whole space, not just the direct sound, but also the reflections and the late sound field of the room, or any space basically. So why go through all this? Why do we want to have 3D auditory displays? For the auditorization case, yeah, you want to be able to somehow present to your customers, for example, of the ones who are ordering your concert hall, how the concert hall would sound. But for an auditory display in general, there are several advantages, I would say, in addition. For one thing, it's if you have multiple sound sources that you want to present to the users, it's much easier to perceive these concurrent audio streams or sources when you have this kind of 3D audio renderings. You can separate them using these cues, and you can focus on one source at a time, shift the attention between the sources and so on. In comparison, if you would have normal stereo sound or even mono sound, even worse than to be able to discriminate between the sources and hear what they communicate to you. Also, I mean, the auditory spatial cues in themselves, they add layers of information, so like the angle and distance to objects. For example, if you have any objects nearby the source that reflect the sound, you can, of course, communicate room size and maybe even shape, and what kind of materials you have on the walls using these kind of cues. And you can basically create a sense of being there in this remote or virtual environment. So that's more on a higher, more abstract level perhaps, but that's something which is, of course, very, very important in a virtual reality situation. And in some, it's more intuitive to perceive sound this way, in the spatial way, since this is the way we perceive sound in real world, in everyday life. That's the way we have taught our systems or auditory system to perceive the world, basically. So there can be a lot of advantages of 3D cues added to auditory displays. Now, some applications. I guess the most obvious application is gaming. And with the advent of these consumer-grade virtual reality headsets, 3D audio is becoming something which everyone can experience. And it's an integrated part of many game engines and so on, this kind of 3D rendering with HRTFs. This is an example that a game called Vader Immortal that you can play in Oculus Quest Rift, which clearly uses HRTFs. They also have actually some auditorization, some room effects added, as you can hear in the film that I'm going to play in just a few seconds. So in this clip, I think you can hear that you can clearly localize the voices and the sound effects that's around you, but you can also hear the shape on the acoustics of this space that you're in. So I'll play you the opening sequence here, some gameplay from Vader Immortal.
better move it, Captain. The Hutts want their spice back. We gotta jump to hyperspace or we're dead. Come on, flip the bypass switches for the hyperdrive. All right, hyperdrive controls are active. Make the jump to light speed. Nice one, Captain. Oh, that never gets old. As soon as we offload these spice crates at Shadow Market, we are sitting pretty. You know, maybe then you can make those repulsor lift upgrades you've been promising me forever. You know, and forever and ever. You know, it looks like we're gonna be in hyperspace for a while here, so feel free to go back and check our loot. You name it. Sky's the limit. Some of our previous and future ports of call.
Right. Yeah. Hope you like that one. It's a quite good game, actually. It's fun. As you could hear, or I think, in my personal opinion, is that the effects are a little bit exaggerated. The sources are a little bit too clear in some source position is a bit too clear in some situations. But the 3D dimension of the sound clearly adds something. It's nice to be able to be enveloped by this acoustics of the spaceship interior and so on. And it's I mean, it's easier to focus on this talking robot when you can hear or turn your head towards it and listen more closely what it has to say. But this technology is not something which is unique for VR headsets. It's been in games for ages. You see this example here now from Half-Life, which has this HRTF-based sound already in 1998. And in that case, it was the A3D format by Oriel, a company which was pioneering this in the early days, which actually sounded pretty good. I would say it's almost as good as this very immortal game. The Oriel company was purchased by Creative later on, so they don't exist anymore, but they had pretty advanced and hardware accelerated HRTF rendering, which also included first order reflection organization, so it was as well as late reverberation. So it was pretty advanced already then. Music and cinema is another field where HRTF's based 3D sound is coming in with the Dolby Atmos format, which you might have heard of. Dolby Atmos is normally a speaker-based format, but using HRTF mixdown, you can actually listen to this type of spatial format only using headphones. And you should have these headphones which has head tracking in them to be able to experience this fully. So these Apple headphones that you see on the picture, they have this head tracking capability, for example. Also the smaller earphones have that as well from Apple. So how this works is, well, it's a bit complicated, but the Dolby format, the Atmos format, it allows, or it has support for both speakers in the horizontal plane, like a normal 7.1 setup, but it also includes height information, so ceiling speakers basically. But what you do when you mix down is that you sort of get the HRTF that corresponds to all these speaker positions, and you filter the sound channels with these HRTFs. So it will sound like you basically sit in a cinema system like this. You can turn your head and listen to different loudspeakers than if you have head tracking. You can also include objects in the Dolby Atmos format, which can move more freely around you. So in that case, you have this direct HRTF rendering that we talked about earlier. Mobile auditory augmented reality is another application that is not so common nowadays. But that we see is something which could be actually very helpful for people. Smartphone apps, they are visual, basically only visual. And if you use smartphone apps in real life, in traffic, for example, it's a bit dangerous basically to use them because that's just in the picture here. You don't know what's happening around if you look at your smartphone and you're supposed to use it to navigate someplace, for example. Also, visually impaired people could have a great help of being assisted by 3D auditory displays in these situations. So Microsoft has made a little framework or an app which tries to help people navigating traffic using 3D sounds. It's called Soundscape. Just a small demo here of how it works.
You can set up an audio beacon at a location displayed by search or a saved marker. When you set an audio beacon, a sound with a certain rhythm will be played when you are heading in that direction, so you can approach the audio beacon correctly. This is useful when you exit a station and are not sure which direction you want to go. It will also tell you how many meters you have left to go.
Beacon. About 50 meters.
So this is something that we are actually currently investigating further in a project in the context of mobility services. Say, for example, you want to help your users to find a robotaxi in a city somewhere. Then you can use this kind of 3D sound beacons. It's like a sound that you're supposed to follow and which guides you to the vehicle. So instead of having to look down at the map, you can basically hear your way through the city and know where you're supposed to go to find this robotaxi. Then you go on a ride, and with the robotaxi you can use sound feedback there as well, of course, since you anyway have your headphones on probably. And then when you arrive at the destination, you walk out of the taxi and you get guidance then on where to go, where to spatially orient to go in the correct direction, and how to get to your final destination. This is something that we are just starting up a project on called EARS, or Enhanced Auditory Reality Scout. It's a Vinoi project together with Volvo Cars and RISE and Polar Print and Arctic Bath in the north, where we will try to develop this app that could guide you to your destination and to different types of mobility services. I promised in the beginning some words on remote operation of road vehicles as well. That's also currently ongoing research at Ictech, together with a lot of industry partners. And why do you want to remote control vehicles, you could ask yourself. Well, it is believed that remote control could be very important in the development and deployment of automated vehicles as a fallback solution, when automation fails or where it's not possible to automate a vehicle, a truck or a car. It could also be that you want to shorten the time to market for services that will eventually become automated, like valet service. Could be remotely controlled at the beginning and eventually be automated. So we have conducted a project called Redo already, and currently ongoing is the Redo 2 project, which are Vinnova projects where Ictech, we are exploring different ways of improving remote operated stations in general, and our focus is of course on auditory displays and how to use 3D sound for one thing to help the operators. And we think that sound in these operated stations could be very important because, well, you need to communicate the normal information and warning sounds that you have in HMIs today, in car and truck HMIs. Sound can also be used to improve the sense of speed and self-motion. You quite decoupled from the traffic and the vehicle. If you're in a remote station, you want to be able to communicate the feeling of speed and self-motion to be able to drive more careful and more appropriate. You could also improve the awareness of the vehicle status, like are there any problems with the vehicle, any loose wheels or something like that. But we think it's also an important way to improve situational awareness using sound and enhance the sense of actually being in the vehicle, the sense of telepresence. And that you could do using 3D sound, we think. So for example, the situation here where the remote car is in an intersection and there are objects around the car. You want to be able to communicate this visually, of course, but you can enhance that awareness by using sound and 3D sound. So for example, you could have sounds of the bicycle and the footstep and the car like this. And I will show you these, play you these examples. Yes, so by having this sound you can get a more intuitive awareness what's around you, and you can hopefully be more prepared of the situation and react more appropriate. And in this research project we have developed this application called LAVA, or Layered Augmented Vehicle Audio, where you can render this type of 3D sound. This is HRTF based rendering, of course. And they can use in a variety of remote operation use cases. You can actually also bring in microphone streams from the vehicle, multi-channel microphone streams, and down mix this using similar technique as I showed in the Dolby Atmos case to headphones, and in such way to get a better awareness of the remote vehicle and the surroundings. And it's actually being tested, similar techniques by KTH, which we work with in the Redo and Redo 2 project. So here's a picture from their setup. They have multi-channel speakers, as you can see, but it's similar idea, multi-microphone setup on the remote vehicle. See it on the pillars here. And the streams are then transmitted to this remote station which I'm currently driving, and you can hear the sound from different directions and so on. So yeah, it's a very nice setup they got there. And do some further experiments on this later on. So conclusions. 3D audio, I have called it binaural sound perhaps also in this presentation. HRTF based audio, spatial sound, whatever you want to call it. But we've seen that you can realistically simulate human spatial hearing using only 2 channels, using headphones to simulate the left and right ear sound pressures. It has a number of advantages to use 3D audio to add layer of information to the audio, but also to greatly enhance the realism and the presence, immersion, and other things of the experience. And you could say that the main use today of this is in computer games and other 3D media, 3D videos and so on, and music for sure. But basically all applications where headphones are used could benefit from the technology, I would say. So these are the concluding words, and if you want to watch the video again, I think it will be available online. But we also have time for some questions, I think. So do you have any questions from the chat?
No, not yet.
Not yet.
But I think they're delayed, maybe 30 seconds. So
Okay.
we have to wait. And they can write it down in the chat at YouTube.
Yeah, you can write down your questions in the chat on YouTube. You are welcome to contact me later as well. I can show you my email address here. It's simply pontus.larsson@ictech.se. So please feel free to reach out if you have any questions or comments or anything you want to discuss 3D sound. I'm always open for that. Let's see if we... I can also show you this slide. We have the references for the videos that I showed during the presentation. So feel free to go in there and have a listen. There are some more examples nice on these channels that you can watch, of course. And the bicycle and footstep and car sounds that you heard, they are not available here, but they are actually rendered by this Lava software I talked about. So you have to reach out to me if you want to know more about that or hear more.
No questions.
No questions. Everything was crystal clear. All right. I think we can close down this webinar then. Thank you all for watching and listening, and hope you have been inspired there now and think about all new applications of 3D sounds that you can have in the future. Bye bye for now, and see you later at another Ictech webinar.